Hello friends, welcome back. Now let us see some common types of data structures. The commonly used data structures are arrays, linked list, maybe single linked list or a double linked list or a circular linked list. It's a stack or a queue or trees, and we have graphs. So what are these? We just look briefly now, and then later each one we look in detail what they are, how they are implemented, what are the advantages of using them, what are the disadvantages of each one, and on so. So starting with an array. Array is a linear collection of elements stored in a contiguous memory locations. So there are basically two types of arrays. In the olden languages, we had static arrays, which had a fixed size, or later new languages like Python, they introduced resizable or dynamic arrays. But commonly, when we talk of array, we actually mean about a static type of array that is more commonly used because the word array was being used morely in olden languages like C and so on. The key operations that can be performed with arrays, so we can access any element in the array in a fixed time. So irrespective of the size of the array, in a constant time, we can access any element randomly from that. But inserting or deleting any element will require shifting the elements and definitely, and because of that, it depends on the size of the array. The bigger the array size, the more number of shifts we need to do while we are inserting or deleting any element. So the positive sides of working with arrays is fast random access. So randomly any element can be accessed at a constant time, and it's simple to implement. Coming on the negative side, if we are working with a static type of array, then at the compilation time only, we have to define what is the size of the array we are going to use. And because we are not sure about how much of the array size is required in advance, therefore, most of the time we try to define the largest possible thing, and because of which most of the time we will be wasting the memory because we have dedicated one fixed amount of memory for a particular array, and if that array is not fully being utilized, then most of the space will be wasted. And though it is unused by the given array, others cannot use it because it is dedicated to that particular array. It is reserved for that array, even though that array doesn't contain even no element, then also no other component can use that memory. So because of that, lot of memory wastage is found in that. And of course, when you are inserting and deleting, it's a order of n. That's the bigger the array size is, the larger number of shifting is required, and hence it is costly in terms of insertion or deletion of any element in the middle. Of course, if you want to add at the end or delete the end item, it's a simple thing. But if you want to insert in the beginning or the middle of that, definitely it will be a tough one. Now, looking at a real-time uh, situation, yeah, we find here uh, books are dumped here, and you can see that they are dumped in some random way, and finding any particular book here is almost an impossible task. But the same thing, if we had put in an order, yeah, that's array of books we have, and if that is put in an order, then uh, finding any book is just one step. So if I want this book, I just go there, pick that book out. So taking a book out or finding a book is one step item. But if I want to insert a book in this place, then I need to shift these books and make space for a new book to be inserted here. So it takes a larger time. The second problem is if the array is full, then we can't add any more items to that because in the compilation time itself we have defined what is size of the array. And here if I see that this compartment is full with the books, so no more book can be added into this. So that's a problem with arrays. If we have predefined size, then if the array is full, then we can't add any more, and we can't even change the dimension, the size of the array, can't resize it because the static version of that has to be defined at the compilation time. So once it is compiled, no more changes are possible. If it had been a dynamic one, then we could have changed in the runtime. So that's a problem with arrays. This problem can be solved using what we call the linked list. It's again a collection of the data. But here, the data is not just put in different locations, they are put in the form of nodes. And here, each node consists of one data and one pointer, which shows to the next node where the next data is. So, wherever possible, we keep one data there, and attached to that, we have a pointer saying where the next data is. So it can be either singly linked or doubly linked. We just look at what they mean shortly. So it says we have A here, then next item is B, next item is C. So we don't have to keep A, B, and C all in the consecutive locations in the memory. They can be anywhere in the memory, wherever possible. But only thing is, make sure that the links are properly shown that this is A, then where the next one is here, which is B, where the next one is here. So that is shown by the arrows. So some sort of graphical presentation we can use where each node represents the data and each pointer represents where the next node is. The key operations performed, you can insert, delete the data at a what do you say, single step if it is in the beginning or at the end. But if it is in the middle, then we need to go till there and then insert it. Therefore, again, order of n is required for insertion. And for searching, yes, you need to move from 1 to 1, 1 to 1, 1 to 1, and definitely it all again needs order of n. The positive sides of using linked list, so dynamic size, yes, that's what we had a problem with arrays because it was static in size. Now we have dynamic size, so there is no prerequisite to define in the beginning what is the size of the numbers we are dealing with, what is the size of the data we are dealing with. So it can be anything starting from zero. As and when required, we keep adding new nodes and add a new data to that. And insertions, deletions are more efficient compared to what we were doing with arrays. Of course, nothing comes freely. And if there is any positive part of it, there has to be the negative side, the other side of the coin, and it cannot be accessed randomly, which was possible with the arrays. Anything you just pick up and take out randomly in one step, you could get there, take it. But in linked list, to reach there, you have to start again from the first node, go step by step, and reach that particular node. Only then you can access it. So, no random access is possible with this, and extra memory is required because in arrays we require memory only to store the data, but in linked list we need additional memory to store the address where the next node is. So here we are storing the data. That's what the array was also using, the same memory. But in addition, we need one more extra space to save the address of the next node, where the next node is, that is where the next data is stored in the memory. Its address we have to write with this node, and each node will have additional requirement for storing these pointers. Therefore, we have to use extra memory for that. This illustrates what uh, memory can be used. So these are the sequence of memories we have, but we don't use them in order. So if it was an array, then first data should be here, second should be here, third should be here, fourth should be here, fifth should be here, and so on. But because this is a linked list, I find a space here, so I dump my first data here, and then if I find a space here, then I can dump second data here, but make sure that connect these two through a link. So there is first data here, then the link shows where the second data is, and the link shows where the third data is, and the link shows where the fourth data is, and so on. So here you don't have to have contiguous memory for storing all the data. You can have a freedom to select any place in the memory. First, only thing to create links from one data to the next data so that we can move from one data to other data without any problem. The other type of data structure more commonly used is a stack, which is again a linear data structure, but this one works on the principle of last in, first out. So whatever the data gets into this data structure last will come out first. And there is only a single access point. So we send the data into the data structure from one point, and from the same point we can take out the data so that we can relate that to the stack of plates. So if you want to add a new plate to this, then we have only one option is to place the new plate on top of this. And if you want to take out one plate, then it is the top of the plate should be taken out, not any other. So the easiest access is adding is on the top, taking out is from the top. So whatever it is, only the top plate is accessible. Either add on the top or remove from the top. So only one access point, and that is what stack of plates is. And this same concept. So whichever plate is put last will come out first. So the bottom plate is the one which was put first. And if you want to take this bottom plate, then you have to remove all later plates. So the one which come in first will only come out last. So the one which has come last in will come out first, or the one which has come first in will come out last. So first in, last out, or last in, first out is the thing. There is only single access point, and this is how our data structure looks like. So adding data to the stack is called push, and taking data from the stack is called pop. And here, if you look at this, it is data 4 which was pushed first. After that, data 3 is pushed. After that, data 2 is pushed. And finally, data 1 was pushed. So if you look at this, data 4 has come in first, then data 3, then data 2, then data 1. And if I want to take out the data, then data 1 will come out first, then 2 will come out, then 3 will come out, then data 4 will come out. So which has come first in was the data 4, and which will come out last will be the data 4. Data 1 is the one which has come in last, but it is going out first. So this is last in, first out, data 1. Or if you look from data 4 point of view, this has come first in, but it is going out last. So it is first in, last out, or last in, first out, whatever way you call it. The meaning remains the same. So that's about the stack. The other data structure we very commonly use is the queue. It's another linear data structure. And now this one is about a first in, first out sequence. It's a queue. Yes, queue, of course. Everybody is familiar with the queue. People stand in a queue. So the one who joins the queue first will get the service first, and so on. So there are different types of queues, like a simple queue, which is a linear queue. It can be a circular queue, or it can be priority queue. It can be double-ended queue, and many more. So we see them in detail in the coming sessions. So that's how commonly the real time example for a queue is people have come for some service, and the one who has come first to the service point will be served first. Who comes second will be served second. Who has come last will be served last. So the one who comes first will be served first. So the one who joins the queue first will go out queue first. So first in, first out is the logic of queue, and that's a data structure model for a queue. Here, on the back end, the queue gets added, so which we call enqueue, and in the front end, the elements are released, and that is the operation called dequeue. So when a new person comes in, he just joins the queue at the end, and the one who is in the front will be served. And once the service is done, he leaves the queue. So this is the element which leaves the queue first, and this is the element which adds into the queue. So the one who joins the queue first will be served first. So this is first in, first out logic. So all these were discussed were of linear type. Then next we have what we call trees. So trees are very good data structures when we want to work in hierarchy. So that's a hierarchical structure with a root node, parent-child relationships and all. So how the tree looks like. So there is a root and then branches out and branches out. So each branch again branches out. So the same structure, but only thing is we show it in the reverse way. We put the root on the top and the leaves go at the bottom. Yeah, that logic is the same. So hierarchy. So there are many types of trees we can use for our applications. So most commonly used trees are binary search trees, ABL trees, B trees, B plus trees. Many are there. Depending on our requirements, depending on the problems, we have to use different types of trees, different trees, their details, their applications, their pros, cons, more are in stock in the coming future videos. So keep waiting for them. So we are into overview of all the data structures. So that's how a tree looks like. So that's the root of the tree. And there's level one. We have nodes at the level one, nodes at level two. So they can go down and down and down. Where any links end, that's called a leaf. The topmost is called a root. Then other things are called inner nodes. So there is one at the end, top end, root, and the bottommost we have a leaf, and intermediate things we call it inner nodes. The key operations, yeah, search, insert, delete, all are possible if it is a balanced search tree in login operations. But if it is not a balanced one, then order of n is required for searching, inserting, deleting, and so on. If it is traversal, that means I just want to see what all elements are there in my system. Then I have to travel in a specific way so that I travel the whole tree. So that is a process called traversal. I can do in many ways. I can do in, say, in order, pre-order, post-order. So various things are there which we are going to discuss in detail in the future sessions. The positive aspects of this is fast searching is possible in case of ordered data like a binary search tree. So we have a natural hierarchy modeling possible here. So if we are talking about a family tree, we can say that parents, the grandparents, then parents, then children, then the grandchildren. So that whole that family structure can be very easily shown if we make use of a tree structure. And that is not easily possible in earlier versions of the data structures like arrays or linked list or any such things. So it's required is a tree. Other end. So balancing is required for better efficiency. So whenever you try to change the tree, when you add a new data to the tree or when you remove some data from the tree may get imbalanced. And to have a better performance, we need a B3 to be balanced. Then we need to keep it balancing whenever there is a change in the tree possible. So there is that's a negative part of it. Yeah, then we have another important data structure which we call a graph, which is a non-linear structure with nodes and edges. So this is the difference between tree and graph is graph can contain the loops, but tree cannot contain a loop. So it will be moving from the root down to the leaf, but graph is a general form where a tree can also be a graph, but every graph cannot be a tree. Every tree can be a graph, but every graph cannot be a tree because graph can contain loops, tree cannot contain. So there are two types of tree graphs. We can be directed or undirected. So this is an example of a undirected graph where the nodes A, B, C, D, E are the nodes, and there is connection between them using the edges. That means there is connection between A and B. That means there is some relation between A and B because there is an edge here, but there is no relation between A and D directly because there is no edge between A and D directly. So we may find some relation via B or via E to D or via A, B, C and come to D or any way. But directly A to D, there is no direct relation. So this is what the graph talks about. And key operations can be traversal, it can be a breadth first search or a depth first search. Then we want to find a shortest path. So these nodes can be the cities or the places in the any town or a city, and these links can be the roads. And from one part of the globe to another part of the globe, if you want to find the shortest path, then yes, graphs are the easiest tools to work with. So the positive side of working with the graphs is we can model the complex relationships very easily. It is flexible for real world networks, so you can just talk about friends and their relationships. And the negative part, high memory usage for adjacency matrices, because I have to represent that A and B are connected, A and D are not connected. To say this to the machine, I need some way to tell it. So I cannot just draw this image and say just a machine to understand it. No, I cannot make machine to see this image and tell it is this image is for human purpose. So it says that A, B are connected, AE are connected, AD are not connected. This all I can understand. But if I want to make my machine understand, then I have to tell in some other way, and that some other way is a matrix form, which we call it adjacency matrix. So this adjacency matrix is one which is of which requires the square of the number of nodes we have. As the number of nodes increase, the size of the matrix increases by a square. So it's order of n square. So if we have 10, then the size of the matrix will be 100. And if it is 100, then it grows to 10,000. If it is 1,000, it grows to million. And that way, it just keeps getting like a rocket. So that's a major problem we have is the memory usage is very high when the size of the graph increases. Yeah, that's a overview. Uh, Array is a linear indexed order. Access is a fixed one. Insertion delete. Yes, of course, it is linear. And linked list. Access is linear, but insertion or deletion can be of constant time. Tree is a hierarchical. Yeah, access can be log n order. Insertion delete also can be log n, but it is has to be in proper order. Graph, there is nothing we can talk about access, but insert deletion can be done in constant time. So just want to see what all we discussed as an example, why data structures are required. So let's take an example of adding n numbers. Say we have four numbers with us, A, B, C, D, and they are located somewhere in the memory. And if I want to add these numbers A, B, C, D, then I have to say sum is equal to A plus B plus C plus D. And if instead of four, if there are five, then I have to say A plus B plus C plus D plus E, and so on. And if there are 100, then I have to keep on writing all 100 elements, A plus B plus C plus D plus everything like that. But as we write in our common mathematical terms, we cannot just say A plus B plus C plus D plus dash 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 dash. No, we cannot write like that. I have to write each element to find its sum if there is no data structure. So I just redefined this data, and instead of calling it A1, A, B, C, D, I can start calling it A1, A2, A3, A4. Then mathematically, I can write here like summation of AI, where I is from 1 to n. So that is mathematical representation. But if I want to add them, then I have to physically take each one separately, A1 plus A2 plus A3 plus A4 plus A5 plus A6 and so on. I have to again physically work on. If there are 100, then I have to start writing A1 plus A2 plus A3 plus A4. So that way I just continue till A100 instead of 100. If there are 1000, then I have to talk for all 1000 elements. That is when we don't have data structure. Now, let me redefine this as a data structure and let me use an array. Now, I can give index to my data. Instead of just saying A1 is here, A2 is here, and all that, instead of that, let me say that A1 in the first location, A2 is in second location, A3 is in the third location, A4 in the fourth location. So I know the location number, so that is what I call index. And if I know this, then I redefine this as an array. Array means they are stored in a contiguous memory. Now I can say this whole thing, if I call it A, then now I can start saying that the first element of A, second element of A, third element of A, fourth element of A. No, it is not A1, A2, A3, A4. I am saying A is an array, and this one is first element of A, this is second element of A, this is third element of A, this is fourth element of A. So once I define this way, then now mathematically I can write this as summation of A of I, not AI. So A of I, now I can put that in a loop and say, let me start with a sum equal to 0. Then let me put a loop from I saying from 1 to n. And then to this sum, I keep on adding A of 1, then A of 2, then A of 3, then A of 4. So I just keep on doing this. So with this logic, what happens was if n is 10, it is going to add 10 A1 to A10. If A is n is 100, then in the same three lines is going to add all 100 numbers. If we have 1000 numbers, then the same three lines are sufficient to add all 1,000 numbers. Here I have to give each of the 1,000 numbers a different variable A, B, C, D like that 1,000. I can simplify that by A1, A2, A3. Can go up to 8,000. But yes, I have to add them manually. But once I define them with a data structure, then my work has become so simplified that in 3 lines I can add any number of numbers provided these numbers are stored in the form of an array. So once it is stored in the form of array, if it is 4 numbers, yeah, A, B, C, D, I can put them A, B, C, D here and say n equal to 4, it will solve the problem. If there are 100 numbers, then I will put these all 100 numbers in this in a sequence. Make sure that they are one after other contiguous locations. Then this will take care of that. If there are thousand, no problem. If there are million, no problem. If there are trillion, no problem. Only these 3 lines are sufficient to solve the problem. That is advantage of working with data structure. Just imagine that we have 100 numbers and we want to add them. Then it will be like using a calculator, read one number, type it on the calculator, plus second number, plus third number, plus fourth number, plus fifth number, plus sixth number. So that way, just imagine 1,000 numbers you are adding. Though they were available on the memory, still you are not able to make use of the processing power of a computer because you are doing everything manually. But if I use this whole thing in a particular data structure like an array, then I can just type out 3 lines, sum equal to 0, and this for loop sum equal to sum plus a of I. It will add all the numbers. So that's a power of data structure. So that's a simplest example. I could talk about using an array. There are many applications. So for every problem, we can simplify our work. I don't want to type all the numbers using a big machine like a computer. So when I have a big machine like a computer, I want to reduce my work to as minimum as possible and make sure that the major part of the work is done by the machine itself. So 3 lines of code I will type. If I have a array, I can add 10 numbers or 100, 1,000, million, billion, trillion, whatever be the size. Just 3 lines are sufficient to get my answers. So that's the advantage of working with data structures. So more details to follow. If you find this session useful, so please don't forget to like and press the like button and subscribe to my channel. And please, if you feel that it is of any use, please tell your friends to go through the videos. So many more issues to follow that was just an introductory part of what all the data structures we have in our future stock. More details individually, each one in detail. We start looking one by one in the coming sessions. So keep watching. Thank you.